Okay, the first function of RTOS is task or process management. Okay, basically in an application, suppose if the application requires a service or it has to be executed, uh, so that has to be managed. Managed in the sense initialization should be done because that particular application should be stored basically in the memory. From memory, those instructions will be placed and then it will be executed, right? And after the execution, like in during the process of execution, several resources or several uh, resources has to be scheduled, has to be shared with respect to the application. So in order to do that, the main function of the operating system, that is the task or the process management. So basically it deals with the setting up the memory space for the task. Okay, whenever that application requires a service, that application instructions or the code should be placed in the memory. So obviously some memory should be assigned for the task, right? So the in this process management or the task management, uh, application or memory space will be assigned to it. That is the first thing. After that, after the okay, after space has been assigned to the task, next is loading the task code. There is a program, whatever we have written for the application, it has to be loaded into that memory space which has been allotted, right? So maybe from the secondary memory, wherever the code is residing, from there it has to be placed in the RAM memory. So that is the first thing. Allocating after that, after your code is in the memory, next is what all resources are required for that. In order to execute any application, certain resources are required. Maybe a display unit is required, or maybe some sensors, some actuators, or some input devices like keyboard, whatever. Some devices are required. So allocating the system resources also is provided by this process management, and setting up a TCB, what is nothing but task control block, okay, for the task or the process termination for the task. And also process termination and deletion will also be taken care by this process management unit. Okay. So what is this TCB? The main function setting up of this TCB, task control block. Okay, so here TCB initially consists of a task ID. Each task, because at a particular time interval there may be different tasks which has to be executed. So basically each task will be given with an identification number. Okay, the operating system will assign one identification number, and also it consists, this TCB field will consist the task state. Okay, task state in the sense the current state of the task. Different states are there, like say ready state or execution state or the block state. Different states will be there. The information of the present information of the task will be stored in the field known as task state. Okay, next is task type, which indicates what type of task it is, whether it is a hard real time or whether it is a soft real time or whether it is a background task. Okay, basically a hard real time, as I have explained you, it is the one which the application should be executed within a time interval, or else it will affect the external environment. Whereas soft real time, occasional failure of the system is manageable. Okay, so type of the task will also be stored in this TCP. Okay, next the priority, that is task priority. Each task will have its own priority. As you know that in an embedded system, in a real time system, always a high priority task should be executed first. Okay, so each task should be given with a priority number, and based on the priority number the execution will take place. That is task priority. Next is task context pointer. Okay, it is nothing but a pointer for context saving. That is, if there is a switching from one task to the other task, there should be some pointer to point at a particular location where the execution has stopped, right? So that pointer, that information will be stored in task context pointer. Okay, next task memory pointers. It is the pointer to the code memory or the data memory and the stack memory of the task. Whenever we say when a memory is assigned to a task, basically there are three types of memory. One is code memory, which basically stores the instructions. Other one is data memory, right, which stores the intermediate results during the execution, as well as the stack memory. Whenever there is a switching, certain data has to be stored in the stack. So each all this memory should contain a pointer. Okay, and that pointer we call it as task memory pointers. Okay, Next is task system resource pointers. So in order to execute any task, you may require different resources. Okay, which all resources are available for that particular system. It has to be shared with respect to different tasks. So in order to point to the specific resources, there is a pointer. That pointer is known as task system resource pointers. Next is task pointers. It in a particular memory, there may be different numbers of tasks, right? They may be, or in general, we can say different TCBs will be there. That is task control block based on the applications. So those tasks also should be pointed, which particular TCB has been executed. It has to be, or which is the next TCB to be executed. It has to be pointed. So that pointer is known as task pointer. Okay, and various other parameters. This is relevant for the task parameters will be stored in this TCB. So basically, task process management. The objective or the need for task or process management is first to create one memory space for that particular application. Once the memory space is created, we have to load that code to that particular memory. Once the code is loaded, next execution will take place. So during the execution, there may be different resources required to execute that particular application. So scheduling or allocating the system resources is also the function of process management, and also setting a TC for each application. One TCB block, that is task control block, should be set, which contains information as I explained you, whether nothing but task ID, task state, task type, task priority, task context pointer, task memory pointers, task system resource pointers, task pointers, and other parameters. And also uh, task termination and deletion is also function of process management. Next function is what I have already explained you. Next function of the kernel, real-time operating kernel, it is memory management. Okay, so in general, the memory allocation time increases depending on the size of the block. Memory needs to be allocated, and the state of the allocated memory on and the state of the allocated memory block. That is nothing but if you consider general purpose operating system, in general purpose operating like what we use in Windows and all, it is block based memory technique. Sorry, it is dynamic memory allocation in general purpose. Dynamic memory allocation in the sense, what is the code size? Based on the code size, dynamically the memory will be allocated to that. So basically, it is a bit time consuming because we need to find the code size. Based on the code size, we need to check which where the memory out of the entire 4 GB of memory, say for example, where which block of the memory is free and where it has to be placed. That particular code has to be placed. Now, instead of going for dynamic in real time, what happens is it is block-based memory allocation technique. Block-based in memory allocation technique in the sense a particular application will be assigned with a certain certain block of memory. So whenever that application requires a service, that entire block will be mapped or it will be assigned to that particular application. Since as we know that embedded system, it is nothing but designed for a particular application. In any embedded system, you consider the number of applications is fixed. We know exactly what are the applications is going to occur in an embedded system, right? So therefore, what can happen is as the list of applications are known to us, for each application or for each task, a particular memory, a set of memory or a block of memory can be assigned to this. So basically, RTOS uses block-based memory allocation, whereas general purpose it uses dynamic memory allocation. So here in RTOS, kernel uses block of fixed size of dynamic memory, and the block is allocated for the task on a need basis. And the block are stored in free buffer. So here in this particular RTOS kernel, which allows access any of the memory blocks without any memory protection to achieve predictable timing and avoid the timing overhead. Here we don't have separate memory protection unit or something like that. Basically, it access to the entire memory locations. So what happens overhead involved in say protecting and checking whether it has got access to that, all that will be eliminated. Okay, so base RTOS kernel assume that the whole design is proven correct and protection is unnecessary. So that is very important. We need to make sure that there will be no bug or no unauthorized access or unauthorized users can get into and change the data. So if that design is perfect, then we can make sure that this memory block or the memory uh, area doesn't require any extra what we call memory protection unit. So we can avoid it. So the overall time required access of the data will obviously be reduced. Okay. So that is the second function of real time, that is memory management. The third function, it is interrupt handling. So as you know that interrupts informs the processor, it tells the processor that an external device or an task which is associated, it requires an immediate attention, right? An interrupt is nothing but whenever you give some input or whenever an external event occurs, it has to be detected at the earliest, it has to be processed, right? Always interrupt is nothing but a high priority task. So it has to be detected and processed. So interrupt can be either it can be a synchronous or asynchronous. Synchronous in the sense, say at every time interval, that event will occur. For example, suppose say if you want to measure the temperature, it is designed such a way that say for every 5 minutes, the room temperature will be measured. So that 5 minutes is nothing but regular interval, right? At every regular interval, an interrupt will occur. That is, at every 5 minutes, an interrupt will occur. What interrupt is that? To read the temperature. So information will be given to a controller or processor that interrupt has occurred at every 5 minutes. So based on that, the reading of the temperature, a program whatever is it, it will be executed. That is known as synchronous interrupt. Asynchronous interrupt in the sense, we are not aware when exactly that interrupt will occur. Interrupt can occur anytime. Say for example, automatic door system. Automatic door system in the sense when a person comes near the door, automatically the door should open. So person coming near our door, it is asynchronous, right? We don't know when the person will come. He can come at any time, right? So that is asynchronous. So whenever such event occurs, that is nothing but an event which will occur uh, at any time. So such type of interrupts are asynchronous. So basically, it has to be detected and it has to be considered as high priority and should be serviced by the controller or the processor. So most of the RTOS kernel implements nested interrupt architecture. In ARM controller also we have seen this topic, nested interrupt architecture. Nested interrupt, or in ARM we have seen a block known as NVS, right? Nested vector interrupt controller block. Where nested interrupt vector controller block here, suppose say a microcontroller or a controller is executing a particular interrupt. Okay, it is executing an interrupt itself, and during the execution of an interrupt, if one more interrupt occurs which is of high priority. Okay, during say microcontroller, we just imagine that microcontroller is executing one interrupt, and during the execution of the same some interrupt, if one more interrupt occurs and which is of higher priority than the present running interrupt. Okay, so what happens? Since it is a high priority, the present running interrupt will be stopped, the execution of the present running interrupt will be halted, and there will be switching from the present running interrupt to the high priority interrupt. It executes the high priority interrupt, and the execution of high priority interrupt is complete, then it will come back to the previous interrupt where it has stopped its execution. So that is known as interrupt nesting. So most of the RTOS will implement uh, will give this service of interrupt nesting. Okay, and we will study about this. That is, this process is known as pre-emission. There are different scheduling strategies for that pre-emission technique. We'll go through it later. Okay, so this is one of the important function, that is interrupt handling. The next function is time management. Okay, uh, that is, interrupt informs the processor that an external device or associated task requires the immediate action of the CPU. And here, as we know that this basically we deal with real-time systems. So any execution or any services should be executed with a given time interval. So this time management plays a very vital role. So accurate time management is essential for providing the precise time reference for all applications. So therefore, the time reference to the kernel is provided by the high resolution real-time clock hardware chip. So we'll have RTC unit. I think you have already studied about the RTC unit in the last module. This RTC unit, it is a real-time clock unit which basically provides the synchronization or the time for the time reference for the execution of any program. So the hardware is programmed to interrupt the processor or controller at a fixed rate if it is synchronous. This timer interrupts is referable as timer tick. Okay, so that is the function time management. So next is say hard real-time system. As you know that hard real-time system is nothing but a real-time operating system which should strictly adhere to the timing constraints for a task. Okay, hard real-time system must meet the deadline for a task without any slippage. In the sense, it has to be executed that particular application, so the task has to be executed within the certain time interval. Okay, if it meets the deadline, then obviously there will be an effect to the external environment. Missing a deadline may produce catastrophic result for the hard real-time systems, including permanent data loss and irrecoverable damages to the system or the users. So that is nothing but it emphasizes on the principle that a late answer is nothing but a wrong answer, right? If you answer late in the hard real time, it is a wrong answer. We cannot accept it. In soft real time, late answer is fine. It is acceptable. Okay. So airbag system is an example for hard real time. That is whenever a crash occurs within the time interval, within a second, your airbag should open, right? If it doesn't open, if it doesn't open, then what happens? It definitely it will affect the external environment, right? Soft real-time, as already explained, software in real-time operating system that does not guarantee meeting deadline, but offers the best effort to meet the deadline. Okay, it may not execute an applications within the deadline whatever we specify. They may be a failure and it is acceptable. Such applications are known as soft real-time applications. That is, missing a deadline for a task are acceptable if the frequency of deadline missing is within the compliance of limit of the quality of the service. That is, every time if it meets the deadline, then we can't call it as an real-time system, right? Occasional failure is acceptable because each system will have something known as quality of service. Okay, in quality of service, that limit will be there, it will be mentioned. Okay, that is compliance limit of quality of service. So the frequency of failure it occurs again and again, then it will not be considered as hard real time. But occasional failure is okay. Soft real time system emphasizes on a principle: a late answer is an acceptable answer, but it could have been done bit faster. This is the difference between the hard real time and soft real time. Hard real time, late answer is wrong answer. In soft real time, late answer is acceptable, but it could have done bit faster. So ATM machine, that is automatic teller machine, is a typical example of soft real time system. If the ATM takes a few seconds more than the ideal operation, nothing bad will happen. Okay. So those are nothing but the various functions of our kernel system as well as different types of system we have seen, hard real-time system and a soft real-time system. And the next step it is uh, what is task, what is process, and what is threads. Okay. So in operating system context, task is defined as a program in execution and related informations maintained by the operating system. Right? It is nothing but a program itself, task, which is defined as a program in execution and related informations obtained by the operating system of the program. So task is also known as, sometimes we call it as a job in operating system process. A program or part of its execution is called a process. Okay, basically you have a task. Task is nothing but an execution program. Inside the task, we call a part of the execution. Different functions or different applications will be there inside a task. So such task we call it as a process. Okay. Say for example, consider that automatic door system itself. Inside that program, inside that automatic door system, we may have different process. Different process like first process to read the door input, the input sensors, right? After that it is read, it is stored in the processor, and from there processing will be done. And maybe the second process, that may be a second process processing. Third process like controlling opening or closing of the door. So task, you have a task. Inside a task we have different process, which is just nothing but a part of a execution. Okay. So the terms task, job, and process refer to the same entity basically in the operating system context, and most often they are used interchangeably. The process requires various system resources, right? In order to execute any process or a task, it requires various system resources. Resources like it requires a CPU for execution, right? A memory for storing the code to the process, and also associated variables and different I/O devices for the information exchange, right? So in order to execute that, various resources are required. So all that synchronizing and scheduling that resources, we are going to study on the next coming topics. So this is the overall structure of a process. As I told you, whenever an application has to be executed, basically we have seen in the last PPTs, whenever you have a task to be executed, a particular memory will be allocated for that particular process and task or task. Uh, so you can observe here, this is a process, right? And various informations will be assigned for that process. The concept of process lead to the concurrent execution of task and thereby efficiently utilizes the CPU and others. That means like this, I may have different process in the memory. N number of processes may be there in the memory. So it can execute in parallel. So concurrent execution is achieved through the sharing of the CPU among the process. That means various processes can be shared with respect to the CPU. Remember, we have a single CPU, but I need to have some scheduling strategies which will give us the feel that the process is being executed in parallel. Say for example, at first time interval, process 1 will be executed. After that, after a particular, say if I consider a simple round robin technique, one time slice will be given. In the time slice, first time slice, the process 1 will be executed. After that, this will be stopped. It goes to process 2. After that, process 3. Like that, it continues in the round robin fashion. That is, we feel that all the process is being executed. Right? Like that, there are various strategies. We'll discuss it in the coming classes. And a process mimics a processor in properties and holds a set of registers. Remember, it contains a set of registers. Each process will contain a set of registers, and in general, it mimics the processor itself. Like it contains the registers like process status, a program counter register to point the next, as you know, program counter holds the address of the next instruction to be executed, whereas process status contains information of the status of that particular process, different flags of that particular process, right? A stack for holding the local variable associated with the process, and the code corresponding to the process. So you can observe here, each process will contain this value. One is stack or the stack pointer, which requires to store the intermediate values whenever there is switching from one process to the other process, and along with that working registers, a general what we call general purpose registers. In ARM controller we have studied R0, R1, R2 like that till up 14 registers we have seen. What we call it as working registers. So each process will have its own working register, that is the intermediate data values will be stored in this working register. Next is status register. Okay, status register of that particular process, which can include like program status words and the status of that particular, like whether it is active state registered, all that information will be in the status register, as well as program counter. PC holds the address of the next instruction to be executed. You can check out this PC is given to the code memory corresponding to the process. So if you consider any process, each process will have this information. That is why it is told this process in general, it mimics the function of the processor. Processor also has the same contents, right? So here the entire memory will not be allocated. A part of the memory will be allocated for each process, and in that memory, these informations will be shared. Okay. So when the process gets its turn, that is for the execution, its registers and the program counter registers will be mapped to the physical registers of the CPU. Okay, is that clear? When this process like this, I'll have different process in the memory. So when this process gets its turn in the sense gets its turn for the execution, right? So this information should be mapped. Whatever information are there in the stack, in the working register, status registers, program counter, it has to be mapped to the processor, the main processor, the main working registers of the main processor. So that process will be given when the process gets a turn, when the process gets the CPU, all this information will be mapped to the processor. Okay, and then the execution will continue. That is nothing but the structure of the process. Next, the memory organization. Already I have explained you. If we consider any memory in a particular process, each memory, it will be divided into three main sections. That is stack memory, data memory, and the code memory. Okay, stack memory, data memory, and code memory. As you are aware, the stack memory holds all the temporary data such as variables uh, local to the process, right? All the temporary memories like stack holds variable local to the process, that is during the context switching or whenever the high interrupt occurs, whenever there is switching from one point to the other point. Uh, this data stack will be stored. It will be stored in the stack. Okay, data memory holds all the global data for the process during the execution, whatever data need to be stored. So that will be stored in the data memory, and all the global data required for the execution will be stored in the data code. And the code memory contains the program code corresponding to the process. Okay, so on loading a process into the main memory, a specific area of the memory is allocated for the process, right? That is, when you load a process to the main memory, certain, as I told you, the block of memory will be allotted for this, uh, for the particular process, out of which it will be divided basically into three sections, that is code, data, as well as stack. And code memory and data memory will be a lower part. Certain memory will be assigned as data and certain memory as a code. Whereas stack memory, it depends on the operating system. Stack memory may point to the top of the stack sometimes, or it may point to the lower to the stack. In most of the cases, it always points to the top of the stack. The pointer will point to the top of the stack. Whenever you are storing a data, the content will be decremented by one, and there the data will be stored. And when you want to fetch it, first it fetches and then the content will be incremented. So basically it means the stack memory grows downwards, or it may grow upward based on the strategy followed by the OS. Okay, coming to process state and transition, I think we'll continue this topic in the next class, process state and transition. So